Okay, let's get started. Looks like everybody's here. All right. Are there questions about the project? Since I ironed out the access issue we had over the weekend. Yes.
1 second, I'm doing that in my bedroom. And the bucket that you have provided in the assignment, that seems like it does not exist in the AWS.
So that was part of the access problem. You have to query it directly because I was under the impression originally that my user and everyone else's users were in the same account. How it works instead is since my account is older, it's separate from the rest of you guys. So what happened was every one of these student users, AWS users, is in the same AWS account except for mine. And because I own the S3 bucket that you all have to use to access the data, I have to give you specific permission to be able to access that bucket because you're in a different account. So when you access infrastructure in AWS across accounts, the permission has to be mutual. In other words, you have to be granted permission within your account, and I have to grant your account permission because the accounts are different. So I figured that out over the weekend, and I apologize for the inconvenience for that because that was annoying. But it's okay. It'll be better on every subsequent project because we don't have to solve this problem again.
So when they're going to do that, like, when I can actually do an S3 bucket.
Oh no, you can access it right now. Yeah. You have to ask for it specifically. So if you do like in AWS S3 LS, the bucket's not going to come up. But if you do an LS on the bucket, you will see something.
On the bucket, big bucket.
On the specific bucket that you're supposed to access for your hello.
When I can see, when this is 535 short 20 including the workspace admission plan, there's nothing like such article or something in system.
Yeah, you have to specifically query that bucket. So yes. Here, I'll show you an example. Okay, so because this is in my account, I see it over here. But if you were to not S2, S3, S, and query it this way, that's not how you're supposed to do it. I use a MacBook at work, and this is Windows, and I have to switch my brain every day. So you have to query it like that. It's just the name of the bucket. It's on the assignment right up too. Okay, can we see it? You got everything? Okay. You got it?
So it's in which Hajin workspace the cursor.
Yeah. So is it not charging? It's not charging. That's a problem. Thank you. It's still not. What's going on? That's better. Okay. Now I know why we're having such performance problems. Okay, yeah. So if you go into my workspace, you should be able to see these are all the things that you're going to need for your assignments. So everything's in here. And because I gave permission to the entire account, you should be able to access this from EMR as well.
Instead of directly that you have provided in the assignment, you have to use those files.
Yeah. So the source for your data sets in your assignment need to be from this directory. So I'm not going to access anything in your workspace buckets. So your project has to work from beginning to end in my account using only this as the initial data source. Cool. Okay. All right. So while I was going over this, it occurred to me that you didn't have a frame of reference for what your performance was supposed to be when running this code.
Oh, you can be one, not even us. I'm not supposed to know with CBS when I look this.
So if you look at the AWS console, you will not see this bucket because it's not owned by your account. But if if you list it out specifically and you ask for it, you will be able to retrieve it. So it occurred to me that you all didn't have a frame of reference for what a reasonable performance of your code would be. This is the EMR cluster I started over the weekend for my implementation of the project I gave you last week. Yes. Well, what just happened? Okay. This thing's taking its sweet time again. What's going on? We look at steps. What? Excuse me? You're okay. There we go. Okay. So my implementation of this assignment took just under 10 minutes. So that's a pretty good frame of reference for how long you should take, even though you have 75 minutes. Okay. So I can go over the development process I used for it. Uh, from here on out, I'm going to be using a lot of helper functions that I define here, just because typing out everything every single time is exhausting, and I'm a programmer and I'm lazy. So I'm going to show you what I like to use. So first, I like to have a parquet function that will take a prefix that you configure and automatically read in a table from that. So I'm just going to say prefix, and then some files equals spark dot read dot, and I'll put this up for you after class. So then we're going to do is, because every time I read a parquet, it's probably just going to be for my prefix anyway. This is taking a crazy long time. So this is the common prefix that we're going to use for, all of our initial data sources for this class. So we're just going to say it's going to be in here, and we're going to make that a prefix. All right, that's the first part. The next part is every time I load in a file or a prefix from Parquet, I want to know how long it takes to load in that. What is going on? Why is there this there? Yeah.
So when I send a big thing to a campaign, and I pass in a location request to it,
Yes.
it is actually creating like a perfect file for every transition, right?
It can create multiple files per partition. Usually it will create just one.
So that's still one per partition. So that's not, I'm not.
No.
So I am referring to when I in one access and read that in. I'm not calling that. I'm not calling it file. I'm calling the the non-folder that all those files are in.
Yeah, you're referring to the prefix.
That's what you call it.
Yeah. So it's just like in S3 over here, we're going to read everything in from these prefixes, but these prefixes have a bunch of different files in here, and every file is going to be read in as one partition in Spark. So when we tell Spark, read from this prefix, and the prefix we're going to pass in is something like link target or page links or anything from, anything from these five options.
It's going to actually be everything within that and put them all together in this little.
Yes. So that's what we're going to see. We're going to expand this a little bit.
So we're going to save a hot day. I'm only telling it the prefix.
Yeah, you're only telling it the prefix, and it will generate the names for you. It'll generate the names of every object that it creates in S3 for you. So you don't really need to worry about that. And when you're interacting with another external data source like Snowflake, because account, the pattern we use is we have our long-term data warehouse storage called Snowflake. And when we want to do like more advanced processing that SQL can't handle, we will transfer that data into S3, and then Spark will read it from S3. And then once we have the results from whatever those analytics are, we write it from EMR back to S3, and then we do the transfer again from S3 into Snowflake. So Snowflake knows how to interpret Parquet files because it's such a common format. And it will interpret them in a very similar way that Spark does. So what I usually do is every time I read in a Parquet, I want to know three things. I want to know how many rows are in the data frame I just loaded in, what's the schema, and how long did it take. So what we need to do is let's actually separate this out. Okay. And so then what we need to do is, let's see, we need to create a SQL table. So first, we're going to persist it. And I realized that I didn't talk about the persistence levels yet. So the persistence level is going to define when you cache a file or when you cache a data frame in EMR, how is that information cached? Where is it cached and in what format is it cached? And if we look at the different options for storage level, You can see a bunch of different things. Okay. So these are the options that are immediately available to you. You can actually create, this is too small. You can actually create one on your own from these options here. And you also have the option to replicate the storage if you want. This is really useful for particularly long-running processes where one of the machines in your cluster is at risk of dying. And so what will happen is when you cache this data frame or this SQL table, it will cache the partition, one of the partitions in one location, and then in a totally separate location, preferably on a different machine, it will cache that same partition again. So if you lose one of your machines in the cluster, you still have a backup. So EMR will automatically allocate another machine for you if a machine dies, and that partition can be copied back over and you can continue running it. I have had machines die in long-running processes before without replication, and it's a complete disaster because in order to actually compute everything, it has to redo the entire process just to retrieve that one partition that was lost if you don't have replication. So really long-running processes, you want the replication. That's not really going to be necessary here because we're using only one instance in our clusters anyway. But this is just something to keep in mind. In our production process, when we're building the identity graph and building the statistics for everything, I use memory and disk too. So it replicates it once, and if we run out of memory, the excess storage will spill the disk. That's what that means. Questions so far? Okay. We also have different combinations of memory and disk only. And so the really interesting part, though, is this memory and disk deserve. Does anyone know what that means? So by default, Spark will cache your data frames in a serialized format versus a deserialized format. Anyone tell me what serialization is? Right. And so in-memory storage, like the way that your machine deals with data in memory when it's performing computations is different from how it's stored on disk. And that difference matters because usually the representation of the data on disk is way more efficient than it is when you actually need to compute on it in memory. And so that's why the Spark default is to store everything in serialized format because it takes up way less space when it's in serialized format than it is in memory. Here's a perfect example. We have a machine learning model in that's serialized to a bunch of JSON files. This is our OmniScore machine learning model for count. And it's this giant random forest model with like 3 million different nodes in all the trees combined. Like it's a huge model. And in total, all of these JSON files that make up the model give it about maybe a gigabyte in total of just JSON. And this is the entire model. When we actually have to load the model into memory in order to use it, that memory usage, even though we're just loading the JSON into an in-memory structure, that jumps up to 6 gigabytes. So it uses 6 gigabytes of memory to hold 1 gigabyte's worth of JSON, which is crazy. That's a huge increase. So memory representation or in-memory representation of data is way less efficient than serialized representation of data. There's a special serialization technique that you can use called zero copy deserialization, which we're not going to go into detail here, but I think it's insanely cool, it refers to when you store information on disk in the exact same format that you store it in memory. And so that basically means you can take a file on disk and then just load it into an array of bytes in memory, and then it's ready to go. You don't have to do any more processing beyond that. Zero copy deserialization is wicked fast. It's so fast. And in fact, I built zero copy deserialization for OmniStore. And what happened with this is, in order to load the model from the original JSON format into memory for OmniScore, that took about maybe 15 seconds from JSON. If you use zero copy deserialization and you want to load it into memory, that took 12 milliseconds. It was 1,000 times faster because you don't have to do any processing at all. You don't have to do any parsing or anything like that. It is ready to go. Of course, the code that I had to write uses all sorts of weird pointer casting voodoo, but we don't have to talk about it. So in general, using a serialized format for your data caching is better, even though the serialization and the deserialization adds extra compute overhead because you have to do this translation between formats every time you want to actually use the data. Even though that's true, it still winds up being more efficient because usually in Spark, it's not the compute time that's your bottleneck, it's the memory. How much memory you have really dictates how efficient your code is going to be or how fast it runs, rather than whether you're doing serialization or deserialization or whatever. So even though there's a slight inefficiency involved in constantly serializing and deserializing data whenever you want to use it, it's still much better than the alternative. So my advice is to always use a serialized format, which is what it is by default. So in this case, we're going to always use memory and disk. Questions on the storage levels? Do those make sense? Cool. Okay. So that's long-term storage, but when we're dealing with it in EMR, you can't have EMR refer to it directly from S3. So we load it into EMR, and then when the storage level says memory and disk, that means memory and disk within EMR on the EMR nodes. So this, whichever thing we read from a Parquet file is going to be stored in memory on EMR. And if memory becomes full, then it spills over to local disk, still in EMR. It just won't cache it. So every time you refer to it, it'll recompute it.
So from this function, are you not going to return this Parquet to do anything with it?
No, my programming style is quite different from the other data scientists that count. I almost exclusively use SQL tables to refer to all of my data frames. I store all of my data frames in SQL tables.
Okay, so we passed it. Okay, I'll just wait.
Okay. So we also need to create a SQL table for this. That's not how you spell replace. And then that's just going to be the same name as the prefix. So what this is going to do is, let's say we want to read in the link target table. What the link target table, or what Spark is going to do. Are you viewing two things at once? No, you're not. Okay. So what Spark is going to do is it's going to take everything from the link target prefix. It's going to read all of them in from the Parquet files in S3, and then it's going to create a SQL table called link target in our local Spark session. So what we have so far is we're taking the files and we're reading them from a Parquet. So this is going to be part of our like DAG execution plan. Then what we're going to do is we're going to take that data frame we just created and we're going to persist it to memory and disk. Then we want to create a SQL table based off of that data frame we just read in from Parquet. So we need to do one other thing. I want this thing to be cached as soon as this function returns. How do we do that? Because remember that Spark is lazy, so calling this function doesn't actually do anything yet. So this is an action that we can take that will force Spark to pre-compute this this data frame that we just stored in a SQL table. And count also gives us the number of rows, which is just nice to know. And in addition to the number of rows, I want the amount of time it took. So what we're going to do is we're just going to print out this handy little message here that tells us which Parquet we just read. So it's just going to be prefix again. It's not how you spell prefix. And then it's going to be how many rows. And then it's going to be elapsed time, which is how long it took to read in. So we're going to do date time dot now minus t. And that should give us the difference between when it started and now. And then what we do is I also want to know what the schema is going to be. Hello? That took a while. Okay. So we also need to start the Spark session because I haven't done that yet. Wait, did it already start? Look at that. Okay, so we defined our Parquet function. Now let's read in our lovely link target table. And this should take about a minute. What just happened? What did I do wrong? S3 path does not exist. How nice. That's probably because I need to add a little slash at the end to signify that this is a prefix and not an object. So let's try that again. Hello? You gonna define this function anytime soon? Okay, so that. And we have another problem. Let's see what we have. That is not. What are you talking about? This path doesn't exist. That isn't true. Oh, it is true because I got the name wrong. There's no underscore in here. Okay, now it looks like it's actually working. So it creates a temporary table, SQL table in Spark that is backed by a data frame.
So you have done now without caching?
Yes. You can create a SQL table without caching. So I persisted first because every time I refer to this SQL table again, it's going to be ready for me. It doesn't have to load it in from S3 anymore after the first time.
But aren't you just about to save it? Oh, you not saving it. That is saving it.
Yeah, so this just saved the link target table in memory. And we can see that it saved the link target table in memory by looking at the storage tab. Okay, so now we have this, this is an ugly name, but it does describe what we're doing. It has link target ID, link target title, and link target namespace. And we have 26 cached partitions, and it's using 2.5 gigs of memory. So this is the link target table as it is in memory.
Why is it better to have it as a table again than just a game for it?
So this is mostly just a style thing. So you can use data frames in your assignments if you want and not use Spark SQL tables. Like I'm fine with that. It doesn't make a difference to me. The reason I do it this way is because a data frame object is tracked like by your runtime in your Spark Connect session. And in Livy, when you're using Livy, this doesn't make a difference because Livy runs on your machine or runs on EMR. But Spark Connect runs on your machine. And so if you use a Spark SQL table, that means you're actually registering it with the Spark Connect server on EMR and not on your machine.
So if you had done this and returned the data frame, all of that would have been returned to the
No, so it's only the reference to the data frame. Yeah, it's just a reference to the data frame. All the data is still in Spark, but it's more of an issue of if my session or if my connection with the Spark Connect server gets interrupted for whatever reason, and this happens all the time at Count because our VPN is really unreliable. And the Livy session timeout is really short. It's only like 30 seconds. So if you have a session with Livy on EMR and you lose your connection for whatever reason and you reconnect again, the Livy session will die and everything in the Livy session also gets deleted. But with Spark Connect, it's different because Spark Connect, even if you were to completely lose your connection with EMR, Spark Connect server is still running. And the Spark Connect session is still there. So any tables that you create in the Spark session will also still be there if you reconnect. It doesn't matter the amount of time, they'll still be there. So it's more of a reliability thing. Because I have a name, I can access it. So it's basically like I'm in the So then you can't use it because now you can't reference it anymore. Questions on how this works? Okay, so this is handy. All right, so now what I also want to do is, this is also part of your assignment, is to take the link target and join it on the pages. So right now we have a Spark.table link target. Okay, let's take a sample here. Okay, so what this is you also have to do your own research on how Wikipedia's data is structured. And I've given the data to you in such a way where the prefixes in the workspace are the exact same name as the tables in Wikipedia. So it'll be easier to look at the documentation. And the column names are also exactly the same. Some of them are omitted, so not all of the columns are there. I've done a little bit of cleaning for you, so you don't have to sift through all that cruft. So it only has what you actually need to do the assignments, and maybe a little bit more than that if you want to do some exploring on your own. But how this is structured is the link target ID is unique for everything you could possibly have a link to. So a page that you link to in this table is only referred to once in this table. So this is the title of the page, not JPEG. These are all objects. Let's do actual pages. Filter, link target namespace equals 0. Okay, and that will give us pages. You wanna, there we go. Okay. Now that looks a lot more like a page. The Asia Pacific Psychiatry. We came up with some interesting stuff here. The Arrow Smurf. I really want to know what that is now. Is that a Smurf playing Aerosmith? I really, of the original French language Smurfs comics. Okay, good to know. Oh, that's funny. Okay, so these are the titles for all of the pages that we link to. This is the ID within this table. So this ID doesn't really have a meaning aside from referring to a specific row in this table. The key here is in the page links table. Now the page links table is huge. It's like 1.6 billion rows. So we're going to load that in right now. And it's going to take like 3 minutes. So if you have questions between now and when it's done loading, please ask. $100 a beer now, $100 a beer. Take one down, pass it around. No one has any questions while we wait? Did I already tell you not to procrastinate on this project? I'm going to tell you again, don't procrastinate on this project. Spark is special because the development iterations in Spark, as in the amount of time it takes to make a change to the code, try something, see the result, debug it, and then try something again, is way bigger than any other piece of code you've written at the university so far. I guarantee you. Andrina's nodding her head. You know this is true. Perfect example is we recently had to make a change to our identity graph, and this was a small change. It was only like 5 lines of code, but we have to make the change, we have to deploy it, and then once we deploy it, we have to actually run the thing, which takes 12 hours. So that happens overnight, and then we come back the next morning, and then we look at it, and we're like, oh, wait, this happened. We didn't anticipate that. And so we have to add another thing, start it again, wait another 12 hours, and then we check it again the next day. So every time we want to try something, every development iteration takes an entire day. We want to try something in this identity graph. Now, it's not that extreme here because the data sets we're dealing with aren't that big and we're using pretty good hardware for the data set size that we're using. But as you can see, this is still like not fast. So it takes a long time to do a little. You kind of just have to sit here and twiddle your thumbs while it happens.
So are you looking for small subsets now and run the code? Like, as a developer, it's like, I think what's frustrating me is that we really need to test small things in small ones.
So that is another thing that I highly recommend that you do in your development process for this project is create a small synthetic data set that has, a bunch of fake data that you've curated by yourself and you already know the answer for the questions you're trying to ask about this data. That tells you that the code that you wrote is actually doing what you want it to do, but it doesn't test at scale, which is half the battle. right? Half the battle is actually getting the damn thing to run without, running out of memory. So that's what I did when, I tested my implementation of the first project is, I wrote the code and I also created this small data set of maybe like 17 different pages. I created all the entries in the link target table and the page table, the page links table and everything. And I tested it on this small set to see if the resulting pairs are what I wanted them to be. So I highly recommend you also do that. But that wasn't the problem when we had to, take a day for every development iteration when we were trying these other things, because you can test whether the code works in this small data set in like a data flow kind of way. You could say, okay, for this small fake data set, it gives us the exact answers we want. So we've tested whether the code is doing what we want it to do, but we haven't tested whether or not we actually want the code to do that thing. So does this actually give us good results? It's kind of like training a model on a smaller data set to make sure your training pipeline works versus training the model on the larger data set to make sure the model works. So at that point, we were making sure the model was working, not the code. That was the difference. Did that finish? Okay, there we go. 1.6 billion rows. Geez, that's big. Okay. So then what we want to do is we have three things in here. We have the page link from, so that is the source node. That is the ID of the page that is linking to another page. And the page link from namespace is the same thing. It's the namespace of the page that's linking to another page. The page link target ID is the ID of the row in the link target table that you are linking to. So there might be many different times the same link target ID appears in the page links table because lots of different pages link to it. Don't ask me why Wikipedia structured its data in this way. I don't know. No, the page link from is the ID of the page, not the link target. So we can also load in the page table. This will take another minute or so. We can also load in the ID of the page table, or we can also load in the page table, and the page table has the ID of the page, the title of the page, and some other stuff in it. And the annoying bit is that in order to actually get the IDs of the pages that link target points to, you need to join the link target table on the page table. So the page has a title. What just happened? Hello? Okay. You need to join the link target table on the page table. The page has, this title over here, and this title is the same as the link target title in this table. So that's the column you need to join on in order to actually get the ID of the page that the link target points to. And so my implementation of project one has like 4 different joins that you have to chain together in order to actually get a list of pairings. And I actually, this isn't available anymore because the EMR cluster is dead, but I saved the DAG of the execution. So this is the Spark plan that Spark created for my implementation of this project. I know it's big and scary. So these are all the different stages for my implementation of this. And the reason we have all these different stages is because we have to join together a bunch of different things to create this set of pairs of mutual links. We have to have the page table, because that's what has the page IDs. We have to have the page links table because that's what dictates, which page links to other pages. We need the link target table because the page links table references the link target table and not the page table for some reason. What was the fourth? And we need the redirect table. So we're joining like 4 different tables together and doing all these aggregations and stuff. The code itself that you have to write is pretty simple. Mine was only like 30 lines of code. But it created this giant hulking beast of a plan that I had to execute. So it looks more complicated than it is, just based off of this vision. So let's do an actual join. That would be fun. So let's say we wanted to know, all right, given a link target ID, what are the page IDs for the link target ID? So given a row in the link target table, we have the title of the page, but we don't have the ID of the page. We want the ID of the page. So how do we create that? Hmm? Yes. So you can refer to the link target table, link target will refer to that table. And you actually have to ask it to refer to a table because Spark is not callable. Yay. So we're going to join it. Joking. I'm not joking. Okay, here's what we want to join on. What do we want to join on? Huh? Yes. So we need link target title and page title. And for completeness, we also want to join on page namespace and link target namespace. Because there's a possibility that in different namespaces, a page could have the same title. Like if you have Aerosmurf and then you have a conversation about Aerosmurf, one of them would be the page about Aerosmurf, and the other one would be a talk page, also called Aerosmurf. Aerosmurf. All right. I've gotten so much amusement out of just looking at the different page titles that I get from random shows and stuff. Okay. So we also know that if we just want to pair up the link target ID and the page ID, not all of this information is going to be useful. So we can filter out a few things just to simplify what the resulted table is going to be. So we can select. I really just want the link target ID, and I also want the page ID. And that's pretty much it. Okay. So now I want to save this into a separate table that we can refer to later so we could build up our other part of the chain. So we're going to do a persist or persist. What should we call this? Link target page. I'll call it link target page. All right. Now you'll notice that didn't do anything. It didn't actually compute anything. So we need to actually force Spark to compute the thing. So we'll say spark.table link target page dot count and then that'll force the thing to actually compute. And so then we can go and look at the plan for this thing to see what it's doing. Look at jobs, click on this thing to see the details of this job. And this is the DAG for this job. It should only be 3 or 4 stages. It's 3 stages. Okay. Okay. So you'll notice that we have one scan parquet, which already happened, but that's included in the stage anyway. So we're scanning the page table, we're scanning the link target table, and we're joining them together. That's what this exchange refers to. Exchange refers to the fact that in order to effectively join these two tables together, we need to send data based on the join key, which is the combination of the link target namespace and the link target title. We need to save everything with the same value to the same partition. And, because we only have one of each value, it shouldn't really be a problem. But in order to actually effectively do this join, the piece that you need for every row from the link target table and from the page table, they need to be in the same place, which is why we do this exchange, because there's no guarantee initially loading the table that they're initially loaded into the same place. So the link target row, like with the link target ID and the link target title, it needs to be sent to the same place that the page ID and the page title are also sent to. So they need to be sent to the same machine so that they can be paired together. Make sense to everybody? Cool. All right, looks like it's done. Okay, so this has, I can't even read that, 37-ish million different rows. Now, you'll notice that this row count is significantly less than the link target row count that we initially got to. And that's because we're using an inner join for this. Can anyone tell me the difference between an inner join, a left join, a right join, and an outer join? Yeah. So the only real differences between left join, right join, and inner join are the things that are included in the result set. So the reason why there are so many fewer members of the link target table after the join than before is because not every page is a link target. Most pages in Wikipedia are pretty small and no other page links to them. And so they're not going to have an entry in this linked target table. So if they don't have an entry in the linked target table, then they're not going to be part of the join at all. And so the result of the join only contains the pages that have an entry in the linked target table. So let's say, the page on koala bears, nobody links to the page on koala bears because everybody likes to ignore koala bears for some reason. And if nobody links to that table, then that table is still going to appear in the page table, but it's not going to appear in the link target table. And so when the exchange sends the data over and then tries to do the match, it's not going to find a match, so it just excludes the row. Things are different with a left join or a right join. So we can take a look at this table. Target to page. Okay, and that gives us exactly what we need to see. Okay, so what if we wanted to take the link target and join it on the page table, and the other thing is that not every link target is a page. We saw a bunch of other files before, I filtered on the namespace. We saw a bunch of like JPEG and OGG files, which are, image and audio files respectively. And so those also can be link targets. So not every link target is a page. we're also doing, that kind of filtering out. So depending on what we wanted to do, we could change between, doing a left join, inner join, and a right join to include or exclude different parts of the tables depending on what we want to do. So let's say we wanted to find a list of the pages, or we wanted to include a flag in the page table on whether or not it is a link target. How would we do that? We could take the page table and we could see, we could do a right join. A right join? Yeah, you could do a right join. And a right join is going to include all of the rows from the page table, regardless of whether there's a match or not. If there is a match, it will populate the link target ID columns with the values from the link target table. If there's no match, then all the values from the link target table will be null. So if we change this to a right join, we try this again, we're going to see quite a few of these link target IDs are probably going to be null. And the amount of rows that we see in the result link target page table is going to be much greater because it's going to include every page and not just the pages with link target. Okay, so that includes way more rows. So that's about 61 million rows. And we're going to see that a bunch of these link target IDs are null. So that's because this page is never actually linked to as a link target. So nobody wants to link to this page. I don't know whether one of those pages with a null link target ID are koala bears or not, but maybe they are. And we should also see that this count should be exactly the same as the number of rows initially read in from S3, which it is, so that's good. We could also try a left join. So the right join gave us all of the pages and possibly a link target ID if one exists. So that was the right join. The right join refers to this table in the join. That's what the right comes from. The left join, what would a left join do? Yes. So a left join would result in a data frame that includes all of the link targets, even if the link target doesn't refer to a page. So then we can see, okay, how many of these link targets actually refer to a page? What's the ID of the page if it exists? If that's the type of link target it is. So we could do something like that and count it again. And we should see a totally different count. The number of rows in the link target page now should be equal to the number of rows in the link target table. So that should be the same as what we initially read in from S3. And honestly, sanity checks like that really help to see if you're doing something wrong. A lot of the time, I will just look at the count of things, and that will really help to see if I'm doing something wrong. Like, am I excluding rows that I shouldn't be? Am I including rows that I shouldn't be? Is something being duplicated even though it shouldn't be? Things like that. So just looking at the count gives me a lot of peace of mind that everything's shipshape. And if the count is different, then I have to explain it to myself. Otherwise, I won't be satisfied. It's part of the verification process because writing tests for things like this can be very difficult. And writing tests for things like this are especially difficult because on the real data set, you don't know what the right answer is. Because in order to know what the right answer is, you have to compute it, which is what we're doing anyway. So it's the combination of, making sure the relationships between everything make sense and using small data sets for testing. So it's a combination of those things that can let you make sure your code works. All right, so now it looks like we have the reverse. So we have all of these link target IDs that are populated, and some of these page IDs are null, depending on whether or not the link target refers to a page or not. So this is the first part of the assignment. I just did it for you. You're welcome. Now you just have to do the rest of it. Yep, we can do outer joins if we want. Honestly, outer joins aren't nearly as useful. I don't think I've actually ever used one, but we can do it just for giggles. So what do we think the size of the outer join is going to be? Yes, it's going to be the union minus the intersection, or it's going to be this. It's going to be the size of the link target table plus the size of the page table minus what they have in common, because we don't want to double count. So we should see nulls on both sides of this equation. We should see nulls in the link target ID, and we should see nulls in the page ID, but we should never see nulls in both. So if we see nulls in both, we screwed up something. Something is wrong. So let's see if that happens. You can actually write a check for that. Spark.table, link target page, filter, link target ID is null, and page ID is null. That's cute. Really? Huh?
If we just say totally definition, we have to show it.
Yeah, filter does not give you results automatically. Filter is just another stage in the pipeline. So it's not an action per se. It doesn't force you to compute any of this. Oh, there's 4 rows. That's problematic. I want to know what these are now. So let's not filter out these. And this is where we get into the fact that Wikipedia's data set, or any data set, is actually kind of garbage. And so it's not going to be like totally consistent with all of your expectations. And so there are going to be these weird edge cases that you're going to have to deal with. It's like, hey, an outer join returned nulls for both of these things. Why did it do that? So let's find out why. So I'm not going to filter out any of the columns. We're going to look at all of the columns for both of the tables in a situation where the link target ID and the page ID is both null. And we're going to recompute this, and we're going to see why Wikipedia is stupid. It differs between SQL systems. We should actually check that. I don't think null equals null in Spark. Like, I don't think null is a valid join key in Spark. I would be really surprised if it was. That would be stupid. I think I have seen instances where Spark will actually try to join on a null. Did it do that? Oh no. This was something that happened at work like 2 weeks ago. So one of our data scientists was trying to I'm not sure if this was the string null or actual SQL null. There's a really big difference between those two things, and how stupid Spark is depends on whether or not this is true. But whether depends on which one is true. So I had a data scientist where he came to me with the question. He was like, "Hey, my process is dying because it's running out of memory all the time, and I don't know what's going on." And what happened was, it turns out when he was sending all of his data to different machines and doing this exchange for aggregation, one of the keys that he was aggregating on could contain nulls. And what was happening is it was sending everything with a null value for the key to the same machine. It was overwhelming the machine. So what we did was, before we did the aggregation, we kind of split the data frame to two different parts. One where the values of the join key or the aggregation key are all null, and the other where they're not null. So we did the aggregations where they're not null. We kind of unioned that with the original data frame that did contain null values for the keys. So that prevented that issue. Huh?
Fine.
Yes,
Like,
I guessed.
by looking at the pivot.
Well, by looking at the code and honestly, my debugging strategy in Spark is just like I know how Spark works and I know what to check. And so like because you don't have access to a debugger or anything like that, um, you kind of just have to look at the log output, see what might be wrong, and then check if that's the thing that's wrong. So I've gotten pretty good at guessing and checking over the last few years working with Spark account. That's my process, and I know that's not a very satisfying answer, but like the more difficult your platform gets to develop on, the fewer options you have for debugging, right? It's like when you're trying to debug multi-threaded code. Like I don't know if I told you this, but I was reading a book like concurrency in C++, and they're like, well, how do you debug concurrent code? When you have a race condition, how do you find the race condition? And their advice was like, you have to read the code really well. And I'm like, great, thanks. I wasn't already doing that. Do you have something else? It was not helpful. Okay, let's see what happened. I want to see. This is going to be stupid. What am I looking at right now? Okay, so it seems like all of this is null, but it's still like joining on the null key. So is it joining on the null key? Oh, that makes me so mad. Okay. We're gonna find out if it's actually joining on the null key. So we're gonna do a spark dot table link target page. Filter link target ID is null. I'm gonna do that. And so apparently, oh, I see. I see what's going on. Wait, no, the link target title has to be null because that's what we're using for the join key. And the names, yeah. Okay. Okay, so it's still giving us a bunch of crap because these are actually correct results because this is an outer join. What? I mean, I can figure this out later, but this is strange because it also suggests that it's joining on the null key somewhere. That's what this means. Because since the join key is null in both cases, that means at one point in this table, they have a null value. Oh, wait, I was looking at the wrong thing. We need to ask link target. That's what we need. We need to ask link target, not link page. There we go. So then we need to ask the same question about the page table. Page ID. I forget what the name of the column is. It's page namespace. Oh, okay, that might make more sense. So these rows with the null values for the keys aren't actually matching on anything, so they just get included in the join result. And then these extra column values just gets filled in because it's an outer join. Okay, that makes more sense. All right, there we go. We're basically at time. Are there questions before we go? I didn't get to show you all the helper functions I have. We'll do that on Thursday. Yeah, don't feel better yet, because I think I've seen it happen. I don't trust Spark. All right, go fight win. Good luck on the project. We can discuss it next time. Wait a second. Oh, okay.